I fell. Oh no, you never. Get up again. That's something hot.
Okay, this is the second to last week. Like I mentioned, I want to give you guys a full 3 weeks, almost 4 weeks, honestly, of preparing for your finals. Hence, this week, and then, or this one, and then next week is going to be the last one. So today we're going to be starting off with the attention mechanism that I promised we will be going over. We're going to break it bit by bit and just build upon the research paper that we'll be replicating until we build the final model. And I don't think it's hard to code. I think it's hard conceptually, in my opinion. But we're going to be doing the coding and the conceptual, all that together. So it's called an attention mechanism. It's going to be based off the human physiological system. So when you look at something, right, your center of attention or your center of vision is going to be what you're looking at. And then literally everything else is going to be your peripheral, and it's going to be blurry. And so we can actually map that more or less mathematically with our machine learning model. So we can tell our model what to focus on, what's important, and what's not important, what's in the peripheral. We can do that mathematically. So the paper that we'll be replicating, that's the homework that I assigned. It's a lot to read a research paper, so I don't care if you guys read it or not, it's a lot anyways. But it's called CBAM. It stands for Convolutional Block Attention Mechanism, and it's like one of the pioneers of attention for a convolutional neural network. It takes two things, a channel and a spatial attention. Channel is which feature or which channel is important, and then spatial, where on this channel or where in this matrix, height by width, are the most important parts. If that makes no sense at all, don't worry, we'll be going, we'll be doing a deep dive for these. Basically, if we have attention, which is here, and we have our input data, which is just like an X, whatever we multiply our data with attention, whatever the output is, the higher it is, the more information we have. You can think of it that way. The lower number we multiply, the smaller the number is, the less attention. The less we need to pay attention to a number like this, and vice versa, generally speaking. So this is the overall architecture. We're going to be coding this. We'll be going through all of this, but all I need you guys, this is the paper. What we're actually going to be doing is coding this separately and coding this separately. The paper, what this architect shows you is that it goes here first, and then it goes here, and then it goes here. So it's a very linear process. We don't need to do that for what we want to do actually. We will just be coding this as one thing and then coding this as another thing. More technically, we're going to be coding two classes, one in the first half and then one in the second half. This paper would be coding three classes, right? It would be coding one class here, and then a third class to take both of them. We're only going to be coding two classes. So this is what the paper looks. This is a more friendly version of this paper. Our input X goes into here, which is this red here, and then this output here goes into this green here, and then it goes to this, which is our final output, which is going to be here. We aren't doing this, like I mentioned. We're going to be doing something like this, or this is going to be a separate one, and this is going to be a separate one, and then the hint is going to be this shuffle block here. Are there any questions on just the generic architecture so far? Cool. So CNN refresh. This is what a CNN looks like. We have our convolutional layer, and convolution is like this squiggly, where we take our input and we have a bunch of features / channels. So the output of something like this would be C by H by W. And hint, remember when we were coding last week? The actual dimensions are going to be the batch by the channel, by the height, by the width. Batch is something that we need to do in coding, which is what I'll get into more of that once we start coding it out. But what we need to know for now is just that the output is a channel by height by width. And then once we do that again, we'll have the same thing. We'll have a channel by height by width, but the channel will probably be a lot longer. The height and the width will probably be a lot smaller because we're going to be pooling using max or average pooling. So that's what we did last week. Where a attention mechanism comes into play are these layers, here and here. So we have our convolution, we have our max pooling, and then we're going to be doing attention. And then after that, we'll be doing another convolution, another pooling, and then more attention. And we can do this n times, where n is the number of layers in our thing. You can also not do attention here and only do attention on the last layer. Or if you have 5 layers, you can do on the last 2 layers. You just gotta play around with it. There's no like right or wrong. It's just test it out, see what's best for your data, and just experiment. So because the attention is here, the input naturally is going to be a 3-dimensional matrix, channel by height by width. And so when I say, in the first part, right, channel attention, which is this part, this is channel attention, and this is spatial attention, as per this diagram. So we're going to be doing channel. We're going to be talking about channel first, and then we're going to be talking about spatial. We might do channel and then code, and then spatial and then code, depending on how we feel. So broadly speaking, channel attention is going to be taking our features in this very basic picture. I have a stack of papers where each paper is going to be a feature or a channel, a matrix. We have a stack of papers. That's going to be our channel dimensions. And then we have a vector, and the vector is going to be multiplied by our, it's going to be like a 1 by n, I should say 1 by c, because this is going to be c by h by w. So every scalar in this vector corresponds to a piece of paper slash feature slash channel here. And that's going to be multiplied to get our output.
Is it just multiplied or dot product?
Multiplied. Yeah. So more specifically, looks like this time, yeah. If we have a 3 by 3 by 3, very basic example, we have a 3-dimensional vector or a 1 by 3 vector. This first number is going to be multiplied by all the numbers in this first matrix. The second number is going to be multiplied by the second layer, and the third, and so forth, where the output is going to be 1 times 0.5, and that's going to be this number here. 4 times 0.5, and that's going to be this number here, and so forth and so forth. So it's going to be a scalar multiplied onto a matrix. And we do that for every single ith value in our vector that corresponds to every single ith value in this channel. Are there any questions so far, like just the generic math on a channel attention? Cool. So, as per the original diagram, this is what we have. I have my pieces of paper that was in my previous slide. We have the original picture that I have. The colors here correspond to the colors on this architecture. So our input is here, input is here. We have this vector here, we have our vector here. We have our output here, which is going to be another c by h by w. The dimensions are exactly the same. So this isn't like c prime, it's literally c and c. Right? It's going to be the same exact ones. And this is going to be here. So what we need to do, what we need to find out is what all this means. And then likewise, we're going to talk about what all this means for spatial attention. So this is this is the journey that we're going to be taking. We have this already. We want to get this, and we need to find out how we can get this vector. And this vector is going to be full of information about which channel, which matrix, which piece of paper is important in this stack of papers. So, any questions on this so far? Yeah, what's up?
So at the top left, the very first, the orange one.
Yep.
That's so basically what happens is you take like an image, and then you extract features from it.
Yep.
And that's what that represents, the features, the linchpin.
Yes, sir. Yes, sir.
And then from those features, we try to extract what the weights are for each feature. That's the second part.
No, what we want to extract is not the weights, but we want to extract a vector that has values in them, and these values are going to say, this is the first value, right? X sub 1. And if this number is 0.9, we're going to multiply this 0.9 by every single value in our first feature, our first matrix, essentially. 0.9 is a high number, which means we're going to be capturing roughly 90% of the information. So it's a lot of information. All of the information in this vector, or in this matrix, is important. Our x sub 2 could be a 0.1. That means 10%. That means if you want to capture 10% of this second piece of paper, it's not a lot. So it's probably not important. And we do that down the line. We already have this as our output for our CNN. What we want to figure out is how we can get these, that 0.9 and that 0.1 I just mentioned to you, and this whole vector, which is this green.
So those numbers, the 0.9 and the 0.1, they tell you like how important a feature is.
Yep.
And is like the what's it called? The module attention. The first one. What's
Channel attention?
Channel.
Yep.
And so channel attention, that's what you use to get that.
Yes, sir. Yes, sir.
And then once you have the channel attention, you multiply by the original. That gives you like a new one with the same dimensions, telling you which ones are the most important.
Bingo. Bingo. Yeah.
And that's the first half.
That's the first half.
Okay.
Yeah. So if we go back to our CNN to expand on exactly what you said, because that's spot on, he was basically saying that the output of a CNN, if our input is a picture of a dog, some of these features could be whiskers, tail, shape, forelegs, blah blah blah. Some other features could be unimportant ones, like what color is the sky, what's the background, is it at a park or at someone's house? The numbers in these vectors are going to determine how important or how unimportant those features are. How important are the dog's ears to our overall output of predicting this is a dog? Probably very high, so it's probably like a 0.9, 0.8, and so forth and so forth. Yeah, that's a good question. So, the way the slides are going to be broken down is that on the upper right corner, I have the channel attention architecture. I'm going to talk about the first step, and the image is going to be here, and I'll be referencing it back and forth. So this is the first step, our input features, and we're in this part right now. So, it says max pool and average pool. It should be technically a global pool, global max pool, a global average pool, because we're taking a global look at it. CNNs inherently have a very local look. If you remember, it's a 3x3 kernel that scans the image, right? So at every time it scans, it's a local view of a 3x3 matrix. This is a global view, which means we're capturing the essence of the entire feature, the entire matrix. Does that make sense? So, if we have in this example, a 7x7 by 3, we're going to take the global max pool or global average pool. These are all going to be aggregators that turn a matrix into a scalar. Output of which is going to be one single number. So it's going to be a 1 by 1 by 3 in this example. And we're doing that for a max and an average pool. So, question, what's the output shape? Oh, I shouldn't say after max pool. After a max and average pool, what is the output shape of this operation?
So there's after it goes through the max pool, it's 1 by 1 and 3, right?
Yep.
And then same after it goes to the average pool, right?
Yep. So that data structure, that tensor that you just said, what would be the final output shape?
So I mean, the width and the height will be 1 by 1.
Yes.
Sure. And then I guess the other dimension is the number of features. So that would be just however many features there were to begin with.
So I'm looking for this number.
And then it should be like, I guess F for features or something. Like C.
Yeah. So what is C?
It's a 3.
Like 3?
Mm.
In this picture?
Is it 6?
So we're taking the global max and the global average pool. And you have this correct, it's a 1 by 1 after a max pool. And then you want to do a global average pool, right? What would be this shape be? It's not 6 or 3. Oh, sorry, I'm sorry. You're right, it is 3. My bad. I'm looking for this number. My bad. This number here.
And it's not 6. Oh, so would it be 3 again?
Mm.
2?
2. Why 2?
Does it come from the fact that you're applying 2 operations?
Yep. Yep. Exactly. So we're doing 2 operations where we get 2 vectors. This is already 1 vector from max pooling, for example. We're going to do an average pool, and we're going to get another vector. So we have 2 things, 1 thing here, 1 thing here. So this together is a 2 by 3. 1, 2, 3. 1 by 1. Any questions so far? Okay. Yeah. So what we're doing essentially is bottling up the most important information from each feature and aggregating it into a vector. So now we get this idea of a vector. How we turn this C by H by W into a vector, which is what we want at the end of the day, right? We do that by doing 2 types of ways: a max pool, which naturally includes outliers, and then an average pool that smooths out outliers to a certain degree, right? You know, average. Okay. Next part, middle part right here. This is called a autoencoder. It's kind of exactly how it looks like. We have a multi-layer perceptron or a basic neural network. We have it here, here, and here. The pseudocode, generally speaking, is we have our input size. We have a small number, like it could be this number. It could be like input, like small number could be like input dash, you know, computer science wise, where this is it's something, right? And then we can divide by any type of number. And the small number would be the same thing, it would be input dash n back to our output. So we're exploding back from.
Are you talking about modular?
Modular, yeah.
That's how it is in Python?
I believe so, right, Oscar?
I thought it was a percent sign.
Isn't that like integer division where you just get the whole number instead of?
That's what that's what I want.
Oh.
Yeah. So we want to take the divide and then get the integer. So what we're doing is turning our input vector, because we have vectors, right? We want to turn our input vectors, turn it into a small space, and then explode it out. It looks exactly like this. We have this is not a vector, obviously. We have our data, our x, our input, whatever it is, our encoder, which is going to be this. This is our encoder line. We also have an activation function. This could be a value. It's small here, physically small here. So this represents a it's called latent space in machine learning terms. Latent space is a high or a smaller dimensional space that encapsulates all the important information from your input. The reason why it captures the smaller important features is because it's small. It doesn't have any room to have any numbers or uses to it. And then we push it back out into the original size through here. So what we're doing is compressing our input, ensuring that we have only important features, and then pushing those important features back out to the original dimension shape. And like I said, this is the pseudocode for it. We have a linear layer. This could be, yeah, so just n in the linear input, whatever it is, small number, activation function, and then same thing. And this is what's happening right here. Alright, this is called an autoencoder, and like I mentioned, it reduces noise. So it only keeps the most important information. It does that, like I mentioned, because it shrinks it down to a smaller dimension, a smaller dimensional latent space. And then we map it back outwards into back the original size of the vector. This is a really, really cool example of what's going on. So we have our forward pass, and then I thought it was going to show the backward pass, but we have a forward pass here, and then we have our backward pass here. I know this isn't the example here because this layer is bigger than the layers next to it, and that's not the case. But imagine if this layer was smaller. What's happening is that data is flowing this way in a regular forward pass, and then through back propagation, data is being flown backwards. So this layer is receiving so much information backwards and forward, and because it's a smaller vector, it's containing only the important bits of information. So this is the operation that's happening. We're taking our vector from the global max pool and the global average pool, and we're running it through this autoencoder. And instead of extracting features or mapping the input data is a vector with channels of information. So each of these contains information about this channel, right? Whether it's the max or pool. And then we're going to be squeezing it through our autoencoder. And then when it goes down to this level, this encoder where it maps to a smaller dimensional space, we're not saying what features are important for a dog or cat. We're saying which channels are important, right? Okay, so we're using the same MLP or the same autoencoder for the max and the average pool. So I like to think of it as this example. This cupcake frosting is going to be our MLP. We have one specific type of tip thingy, and we're going to be pushing something through it. With this same tip, the thing we're going to be pushing through is our max pool vector, which is it could be a pink frosting, and then our average pool is going to be pushed down as well, and that could be our yellow frosting. The reason we want to use the same MLP instead of a different MLP for max and average pool is because we want to have a very concentrated, generalized MLP that will perform well on max and average pooling. This also reduces computational complexity, but the general idea is that we want a model that can perform well on two different types of aggregations. Max pooling vector and this average pool vector. Are there any questions on this so far?
So using the analogy that you gave, the MLP would be like this frosting funnel?
Yep.
Okay, cool.
No, sorry. The MLP will be the pipe and the bag.
Yeah, okay, cool.
The frosting would be these vectors. We're going to be pushing a blue frosting to get the same type, just a blue frosting. And then we're going to push another pink frosting, and that's going to be this other different vector,
Right.
through the same baggie to get the same tip.
Yeah.
Yeah.
Cool.
Yeah. Okay. And then this final part is, or not the final part, but the next part is this part here, which is this here. Very simple. We have our vectors, right? We have a vector of an average pool and then a vector of a max pool after the MLP. Remember, this is going to be the same dimensions. What do these dimensions represent in the vector again? The dimensions of the vector represent what?
The number of weights that you're multiplying?
Like for max pool, what you're doing is, I guess you're taking all the features and then you're taking the biggest ones?
Yeah. So after we do our MLP with a max pool and then the global average pool from here, like here's the max pool, right? We go through the MLP and we have it here. We have the average pool, we have it go through the MLP and we have it here. So this is this is a very generic example. But imagine it looks like this. And this is a 3-dimensional vector or a 1x3 matrix. What does the number 3 represent in this example?
You want to focus.
So I'm wondering what this 3 represents.
Is the maximum for a given channel of a feature?
No, almost. I know what you mean.
Mm-hmm.
There's like I'm looking for one word.
Is it 3? Does it come from after you multiply the standard papers with the decimal number between 0 and 1?
Not yet. We're still trying to find that vector. The 3 represents the number of channels from our input data. Remember? So I ask because we need to keep track of what the data means and the shape of our data at all times, so that when we're coding it, we can keep track of what's going on. So remember, in our input shape, we have a channel by height by width, and then after we do a global max and a global average pool, we have channel by 1 by 1, and we have 2 of these, right? Hence these 2. One of them goes through here, and we have that there, and then the other one goes through the same process, and then we get that here. And so far, and that's where we're at right now. We're here. So we're here. And so what we still have is something by channel by 1 by 1, where every single number here in this example is 3. Is going to be the number of channels all the way from our original input.
That makes sense.
Does that make sense?
What does the NLP do again? Like first, you have your original image or whatever, which is like C by H by W, and then you extract the features only, like you turn them into scalars or something, max pooling or min pooling.
Yeah. So, did you understand what we did here with the? Okay. So the MLP is this type of MLP is called a autoencoder. An autoencoder is a way to take whatever vector we have, because we have a vector, as I mentioned, we have a vector.
And that'll be like the max pooling and the average pooling?
Yeah, so this vector is going to have,
that one's going to be the C by 1 by 1.
yes. So the input for this is 1 C by 1 by 1, which is a vector, and another C by 1 by 1, where this could be your max pool vector, and this could be your average pool vector. And these are all going through this here. Yeah. And so what comes out of it, like I mentioned, is going to be a vector of the same exact shape, hence this white is the same size as this white vectors. And it's going to tell us what's the most important channel between our max and between our average vector.
So it's gonna like take one of the C by 1 by 1s and like emphasize the strong ones, de-emphasize the weak ones.
Yep, exactly.
Just to like make each one more poignant.
Yep.
Okay.
And then the ones that are important, then we can say shut up.
So it like transforms one of them to
Yep.
like extract more information.
Exactly. It transforms it. Yeah, that's a great way to put it. So it's the same dimension. So if we talk about like this 3D space, we have this that is here, this vector that points in this direction from the origin, let's just say, and then we have this vector, and let's just say we want this vector to point in this direction, right? So we need a way to move this vector to point in this direction. Geometrically, that's what's happening here. Theoretically, what's happening is we're moving it because this direction vector, or this vector has more information, or it's more aligned with our output. instead of this vector. Yeah, so that's more of the physics side of it. Yeah. And so like this is the pseudocode, and in the linear, which is a matrix multiplication at the heart of it. It literally is matrix multiplication. And if you guys haven't taken linear algebra, well, first of all, the one that PCC offers sucks, but the matrix multiplication, all it does is a linear transformation. That's all it does. It just moves your data. So if your matrix is there, we want to move it to there. We do that with matrix multiplication. Now this is a 2D example, but if you have a 3D and it lives here, and we want to move it to here, and we want to switch the increase or decrease dimensions, we can do that as well with matrix multiplication. So that's what it's doing here in a geometric sense. But I like to think of it as mapping the data into a smaller dimension, lane space, which is here, and then you map this small dimension back to the original size, which is here, by saying what's important and what's not important. Yeah. So after that, we still have vectors. We have our average vector and our max vector of the same exact size from here, which is going to be channeled by 1 by 1.
So those two, like the blue and the green, those are the original size, but like just more after running into the encoder decoder, they become more emphasized with these.
Exactly.
And it's like you're reducing the noise basically.
Exactly. That's exactly it. And then we add. That's it. Add them. Adding, like I mentioned, is more. You're adding soup. You're adding more broth to the soup. So you're not taking anything away. Adding is a way for us to. When you guys do like derivatives, you guys are doing partial derivatives. When you guys take a partial derivative of something that you're multiplying, you're basically treating it as a constant, right? So it would basically be the same thing. I'm sorry, this would be just y. For those that are taking Calc 3, I think this is right, Jamal? Oh, Jerry, is this correct?
Yeah, I think so. Because you're taking the derivative of.
With respect to x, or the partial derivative of x, it would just be y, right?
That's right.
Yeah. So, taking the partial derivative like deletes something when you multiply. In a similar sense, you're doing the same for adding. So it's the same thing for a back propagation. However, for a forward pass, when you multiply something, like 0.5 times 6, you get 3, right? But if you get 0.5 plus 6, you get 6.5. So numbers aren't being decreased, unless it's a negative number. Generally speaking, the numbers are going to be increasing. So when we're adding our two vectors of our max and average pool, we're not losing any information because we're adding. If we were to multiply, we would be losing some kind of information. So that's that behind adding, combining information. Of course, there are multiple ways to combine or aggregate data. So at the very end, we get a vector. It's still going to be channeled by 1 by 1, and that's going to be here. Finally, we take our activation function. I think it's going to be a sigmoid function, I'm pretty sure. We'll look at the paper right after. But this x should actually be called x sub I, because we're going to be taking every x sub I, 7, negative 6, 2, and running it through this function. So we can get a number between 1 and 0, or 0 and 1, I should say, where the higher the number is, the more important the feature is. This is half. This is really important. Not that much important. Really not important. This is the graph that will look like. The higher the input number is, the more important, or the more we want to keep the information, and vice versa. The lower the number is, the less we want to say it's important, because it's going to be like a low number, like 0.1 or 0.001 or whatever it is, right? Also, this function is good because it creates a really smooth gradient, and so this is going to be very helpful for back propagation, but that's not that important. Any questions here? We're just taking this vector that we just added and running it through our activation function at every x sub I.
And that's how we find our vector that's gonna tell us how important our features are.
Yep. So this is the green vector in the very beginning. This is this. This.
So the
Yeah.
-5 and you said that the dimensions are channel by 1 by 1, right?
Yes.
So if 3, like you said, represents a number of channels,
Mm-hmm.
then shouldn't -5 and 4 actually be 1 and 1?
Right here.
Because you said the 3 at the top represents the number of channels, correct?
Yeah.
And if the dimension should be channel by 1 by 1,
Yep.
then shouldn't -5 and 4 be replaced by 1? Why is it -5 and 4?
That is a great question. So she's asking why I gave you guys dimension shapes in such an odd way. It's because that's how a computer programs it. So there's the linear algebra pure math way, where this is literally just a 1 by 3 or just a 3D vector. The reason why I say a channel by 1 by 1 is because when you guys code this out, this is the output. And they mean the exact same thing.
Mm-hmm.
So you do have a 3 by 1 by 1, and then a 3 by 1 by 1, or you call it a 3D vector, or you can call it just a 1 by 3 matrix. These two are more like mathy. This is more PyTorch-y. And so the reason why I said it this way is because when we code it, this is what it's going to give us. This is what it's going to give us. So we have 3 different ways of saying the same exact thing. Whatever is better for in your head, you can do, but they do all mean the same thing. But just when you're executing it, it's this. Now, why would it be? Why the 1 and 1 in general, right?
Mm-hmm.
Well, the 1 and 1 stands for a single number.
Mm-hmm.
So we have a single number. I don't know. Let me try to draw. So we have a vector that's 1 by 1, and then this is channel. So this is like literally a single number. Like it could be 6, 7.9, 1, 2, and that's gonna be our C.
Mm-hmm.
So 1 by 1 stands for the fact that we have one number in the height, one number by the width, so just a single scalar,
Yeah.
and then the depth of that.
Okay, that
Yeah.
makes
So
sense.
basically, in the matrices, the blue, the green, and the red, each row is the number of channels.
Yeah.
And so
Well, not
basically
the number of channels, not the number of channels. It's
individual channels.
the individual channels.
So like each row is basically each slice on that diagram, like
Here, yes.
the this slice. You know what I mean?
For this diagram,
For the one you drew.
this one.
Yeah.
Yeah. Mm-hmm. Yeah.
But why is there like 4 rows at the end?
Oh, that's just I should have put 3. That's just my bad. Yeah. This should have been 3. If we're trying to stick with continuity.
Mm-hmm.
Now, in terms of the slice that Oscar mentioned, this number or this dimension is going to be the same dimension as this. This is a C by 1 by 1, and this is going to be a C by H by W. So the C and the C here has to match. So the slice for you don't do that. So that's channel attention. Let's see what we got. Okay, so to put it all together, this is exactly from the research paper, by the way. it's this image, and it's this LaTeX. LaTeX is the typey stuff in order to make your math look like this, by the way. LaTeX. It's spelled latex. So, to review, we are input feature, which is we look in the book, paper called F. F is C by H by W. We do an average and a max pull to F. And then we run it through our autoencoder. They acronym it MLP, or multi-layer perceptron, which is a very standard way as well. And then we added it here, which is adding it here. Once you finish adding these two together, then we're going to do a sigmoid function at the very end, which is here, indicated by this thingy, indicated by this thingy on the LaTeX. And then this final is going, and then this is what we get at the very end, this vector. Now this is the vector that this is the trouble that we just went through. This is the same exact thing, this bottom one, except that in the paper, they said like W sub O and W sub 1 are both shared inputs, and the value activation function is followed by dot dot dot. The reason why I just included it in the slide is because shared. If you guys remember, I did say that we're using the same exact piping bag, the same exact autoencoder for both our max and average pool vector. So that's why I included that. Otherwise, it's pretty, useless. But if it was different, I assumed it would say like W sub 1, W sub 2, or whatever, and then this would be a different one. But it's a shared MLP. Any questions? So I'm thinking of coding this with you guys right now and then doing spatial attention, or doing spatial attention and then coding both of them together. Do you guys have a preference on what? Does it matter?
Do we go for spatial attention first?
Yes. Since you're the one that recommended it, yes. You guys probably already know the dimensions. I was gonna ask you this, but I think you guys know it. We can hold that. So, spatial attention. Generally speaking, we have the same exact concept, but instead of a vector, we want to get a matrix. This matrix is going to be multiplied by every single one of our input features. So imagine if this is a feature. I know these are actual pictures, not abstract features. But imagine this being multiplied by this, multiplied by that, multiplied by that. And then, the green is like 0.9, 0.6, 0.7, stuff like that. And that's where the important parts of our feature are going to be. So this is very different than channel, because we have a number multiplied by the entire thing. Here we have a matrix of H by W multiplied by every single other feature that has a shape of H by W. It has to have the same shape, obviously. You can't element-wise multiply two different matrices of different shapes. So this is what we need to create, this one right here. Alright, here's what's going on. We have our input, which is the green. We have our pink, which is here, which is our end goal. That's where it belongs on the diagram. And what I'll be talking about is this. It's a lot smaller, it's a lot quicker, I think, than channel attention. But this is what we have going on. We need to find out what the numbers are for this H by W matrix. Any questions on the difference between spatial and channel attention?
Oh, one quick question. You have the encoder and then the decoder. What was the name of the thing in the middle?
Oh, the entire thing is called the autoencoder.
Oh, okay.
Yeah.
But there wasn't a name for the middle?
No, there wasn't a name for it. Encoder, decoder, and then the entire thing is called a autoencoder.
Okay.
But this is just there's no name for it really.
Is it the hidden, is it the hidden on this,
The hidden thing?
yeah, you see this, the dog on the right?
Here?
Is
This
it
one?
the hidden?
Technically, yeah. So a hidden size is the layer or layers between your input and your output network, or your circles, or nodes, or whatever you want, however you want to think of it. The thing about, so it is technically a hidden size. You could think of it, because you have your output. You have your output here, and your input, and this is your hidden size. So that is technically correct. Yes.
So there's a bunch of stuff going on right there. The size of it doesn't like indicate that there's a little bit going on.
Well, this is I did this example. It's not the best example for an autoencoder, because an autoencoder by nature, the middle part is smaller by design. It's purposely smaller because you want to map your input data into a smaller latent space. By doing so, you are reducing the noise and only in keeping the important information. Yeah. But yeah, no, it is technically a hidden layer. Yeah. So, let's take a break, and then when we come back, we will discuss the spatial attention. If you guys are okay, so Cyrus's question is a great one. Fantastic. I love it. There's an issue with LLMs called a context window, and the context window is exactly how it sounds. A context window is the length of your conversation. This is one token, this is two tokens, this is a third token, yada yada yada. The better a model is, the longer the context window is going to be, right? So this, for example, could be a 50 token context window. DeepSeek V4, their latest model, absolutely crushed the leaderboard because it has a 1 million token context window, which is the entirety of the Harry Potter series. So if you ask DeepSeek V4, you ingest it with the entire Harry Potter series, and you ask what's on the 5th book, paragraph 3 of page 600. It ideally, according to the website, should know exactly what the word is. That's insane. That's absolutely insane.
That is insane.
Oh wait, I have on our Notion the extra fun learnings.
Yeah, you have a video.
I do have the video. I put it up. Well, this is a new video. Last week I showed you guys a video that was around, I think, 3 months old. This new video, and this is how fast the landscape is changing, guys. Like, it's crazy how fast this is moving. This one. This video is the first one. This one's pretty cool. It's really, really cool. No, sorry. This is the one I talked about last week. So
Yeah, that's the one I saw. So now it's old.
that was old already. This one's the new. This is really interesting because they talked about this YouTuber broke down the entire DeepSeek V4 paper. Not only did he talk about how to get a context window of 1 million tokens. So the way they did it is by breaking it into 3 different segments. They broke it down into like the paragraph level. What's the most important part about this paragraph? What's the most important part about this sentence? And what's the most important part about this chapter? Broadly speaking. They didn't actually do that, but watch the video, you'll find out. So they chose 3 levels of granularity, and they mix and matched those levels, and they found out that by mixing and matching those 3 levels of granularity, they were able to get a really, really, really large context window while also being computationally efficient. The math they did for this is like absolutely insane. So that's like around the first half. The second half, if you guys are interested in like electrical or computer engineering, is I don't know if you guys have seen something like this before, a GPU cluster, or you've seen like a data center that looks like this. So this runs, the code to run this is called a kernel. The industry standard is the one that NVIDIA has. I forgot what it's called, but it's like industry standard. You don't really mess with it. It's like saying you don't mess with like C++, you don't mess with Python. It is what it is. These guys coded their own quote unquote C++ to run their own this. This is to bypass the American. So Donald Trump made it illegal for Nvidia to sell the best Nvidia chips. So they need a way to still process all of their stuff while being efficient. And the only way they found out the only way to do so is to rewrite the code from scratch.
So they created.
Crazy.
They wrote their own chips basically.
Yes, they rewrote how to process their chips. So they got the same chips, secondhand, lame ass, B-tier chips from Nvidia or whatever, and they're like, okay, if this is all we have, we can't mess with this. We can only mess with how this works. So let's do that instead. And so
They took like secondhand parts basically, and then programmed their own like kernel
Made it way
implementation,
better.
made it way better.
Yeah.
For like a tiny fraction of the cost. Basically.
Yeah.
That's
Yeah,
crazy.
because they were thinking, they thought that DeepSeek somehow, snuck the NVIDIA chips in.
Yeah.
But that wasn't the case. They just remade their own.
They just have better engineers apparently.
No, they have crazy engineers. Like imagine the engineering that DeepSeek has with like the best NVIDIA chips. Like China would win. Like it's obvious China would win. You know what I mean? I'm not even trying to be biased because I'm like Chinese, but like they would win.
We knew it.
Yeah, no, I'm a shill. I'm a CCP shill.
The thing that you're mentioning, like how they kind of made it from scratch, China, many places in China, they also started being able to modify graphics cards directly by making factories. So they
That's
call them like
crazy.
Frankenstein GPUs. So they literally just have factories to modify like older American GPUs to make them stronger.
Yeah.
They somehow managed to, I think they were able to add VRAM to a chip.
Wow, I didn't know that.
For the
crazy.
context, for like the context window, where does that get stored? Like when, you know what I mean? Like where do they place the context window?
So the context window is something that you manipulate in your model, not something you manipulate in your GPU. So this video this video goes over the paper that they released, and this paper is like it's like fucking 30-page long paper with like 20 authors, and the first half is about the model, and then the second half is about the GPU and like what they did to make GPU faster. So the first half is purely linear algebra, you could say, purely math, I guess. And then the second half is electrical and computer engineering. Yeah. But very fascinating stuff. Okay, and so the cool thing is, DeepSeek v4 is, I think it's free, right? I think DeepSeek is free. I'm not sure.
It's open source. Yeah.
Open source? Yeah. So it's open source, which is absolutely insane because the level of benchmark that D4 was able to get is on par with the paid stuff. So if we look at these numbers, a lot of these models, Claude Opus, GPT 5.4, and Gemini 3.1 Pro, obviously, are all paid. V4 is open source, so you guys could download this and run it locally, and just buy a GPU or use cloud compute, and you could run your own version. And like, look at the benchmarks. It beats. I don't know what these benchmarks are honestly, but it's beating all of these. It's beating all of these. It's equal to these. Got like third place or second place, and it's comparable here.
Those are the different different companies that
Yep.
test them, right?
Yeah. So one's Claude, so Anthropic. One's ChatGPT, so OpenAI, and the other one's Gemini, so Google DeepMind. And it's like on par with the benchmarks for all these other companies. As a Chinese company, that's crazy, dude. And there's another really cool. Okay, I don't know.
America has a lot of red tape, though. We don't allow a lot of things.
You think?
Yeah, I think so.
I kind of agree because also like, I feel like in China you could train your model on anything, whereas in America, like, I think like Disney sued OpenAI because they're like, you're stealing our art or whatever.
Yeah,
You know?
that type of stuff.
Yeah.
Yeah, there's no copyright in China.
Yeah, so you're naturally gonna have like a better training data set. There's a test called the Putnam. It's like one of the hardest math tests in the world. DeepSeek v4 is one of two models that got all the questions right from this math test. I think the other one's Kimi. Have you guys heard of Kimi? Yeah, so that one's a really good AI model, and that one's not free, I don't think. You have to pay for it.
Kimmy, never heard of Kimmy.
Yeah. Yeah, so I think they're from a Chinese company,
Mm-hmm.
but their benchmarks are also really high. Haven't used it though, but yeah, I just wanted show you guys what's happening. If you guys want to watch it, it's going to be this one. I call it New.
So what about the one? Oh, so it wasn't the one below? Deep Sea V4 analysis?
This one is on the same exact model, of course, but it doesn't talk about the in-depth like math. Like this one, like this guy actually like, named the algorithms that these papers are using, and like I mentioned, so this paper, this company in general, just made LLMs a lot more efficient. And this guy named like, oh yeah, so they use like this algorithm and like this proof and like this theorem from like these papers like decades ago. So this guy goes more in depth. Yeah. Okay, so you guys can find that video there.
The crazy thing is that, you know, this is like humanity just pushing and pushing and pushing and going.
Yeah. So a couple of months ago, me, Jamal, and a few other friends went on a hike, and we saw a rocket, like a SpaceX rocket, and like I don't know, they were getting like, oh my god, like this is so cool. They were reporting it, and I was like, I don't know if this is that cool. To me, like the DeepSeek V4, that's cool. Like that. I don't think it's super biased right now, but to me, that's the pinnacle of human engineering, dude.
But it all is.
It is. I know.
The rocket is like, it's pretty crazy to leave our, you know, what it takes to leave our atmosphere is pretty
Yeah. Well, especially the SpaceX, that they like fly it back down and they reuse the rockets.
And that's crazy.
That's crazy. they're both really cool. I'm just being biased. Okay. So spatial attention. To recap, what we're generally trying to do is find a single matrix, this pink one, and what we have as our input is f prime, which is, you can just think of it as f, where f is the same exact dimension as our original input. It's a c by h by w, and if we go all the way back to this one, the attention mechanisms are going to be placed here. So the inputs are going to be whatever happens after a convolutional layer. Also, you can actually put your attention block here and then do a max pooling afterwards. It doesn't matter, you can play with the architecture and try out different things. But let's get to spatial attention. We have our input C by H by W. We want to get a single matrix that's an H by W. I'll be talking to you guys about what's happening in between. Okay, first layer, right here. We are doing what's called a inter-feature or interspatial aggregation. So this image is kind of deceiving because I'm only talking about, sorry. Okay, we have our input feature. It's C by H by W. C by H by W. And we want to find the max and then the average pool of this first pixel. And then we're going to do the same thing for, and then we're going to treat this entire thing as a vector. And when we get the max pool, we're not getting the max pool of this H by W. We are getting the max and then the average of this vector here. This is a vector of, like I mentioned, of interspatial features. Spatial because this is a space on a matrix, like a dog's ear or a cat's eyes. Inter because it's intertwined or it has an interrelationship with other features. Does this make sense? So this is the vector we're going to be looking at. Instead of looking at H by W, we're going to be looking at this C dimension. So we're going to find the max pool of this, and that's going to be a single number. And then we're going to do average, and that's going to be another single number. So that's why you have this orange and this blue, because one of them, this blue is, let's just say the blue is the max, and then this orange is the average. And these hard brackets means concatenation. So we're concatenating two matrices to get a 2 by H by W. Does this make sense? Okay. The max and the average has the same exact idea or concept as before. What we're doing as before is finding a way to just aggregate data. In this example, or in this way, we're doing a max and an average. Two different ways of aggregating, two different ways of saying what's the most important feature, or how can we turn a bunch of numbers into a single number. So, like I mentioned, we're going to be doing these operations for a max and an average pool, but instead of doing like a global one, it's going to be through this spatial vector, if you will. So this is going to produce one number, and that's going to be this upper left number, and then we go down the row, and so this next number is going to be looking at this vector here of top left to the second, and then that we're going to find the max pool. That's going to be a single number, and it's going to be the second number here. And we do that all the way across until we get a matrix that's a 1 by h by w. We do the same thing but this time do an average instead of a max, and to get another 1 by h by w. And so when we concatenate them, we get a 2 by h by w. Does this make sense so far?
Yes.
Cool.
2 by h by w.
Do you understand how we got to the number 2?
Because you did it twice, similar to the
Yeah.
last one.
Yeah, two different operations. One's max, one's average.
I was thinking, wasn't the last one 2 by 3 by 1 by 1?
Yes, it was.
So why didn't we get that this time?
We didn't get that this time because the operation that we're going to be performing on is along this channel dimension. Whereas before, what we did was max and average pool on this matrix. And so that's going to produce a number, hence 1 by 1. And then the C, which is the 3, so 3 by 1 by 1, which is so C is the number of channels. Then the 2 is the max and the average pool for 4. In this one, we're doing the aggregation along this vector, not along a matrix here. Yeah. So here we have the max and average pool concatenated. So we have two matrices. And all we're doing is doing a convolution. Same exact convolution that we talked about last week, where we have our kernel and we have our input data. Our kernel and our input data are going to be two-dimensional. So when we code it out, we actually have to put that the number of input channels is 2. Why is it 2?
One for the max and one for the average pool.
Yep. And so this is what it looks like. It looks like this. It looks exactly like this, where we have a 2 by 2 by 2, 2 channel, 2 high, 2 width, in this example. And then we put that in our input, and then we just take all the information, we multiply 0 by 0, 1 by 1, 2 by 3, 3 by 4, and we get our input data here, and we get another input here. Remember, we want a flat matrix. We want a 1 by height by width, and so in order to do that, we sum it up, or like the computer on its back end sums it up. So if we're coding this, we're going to code out a convolution, a 2D convolution, because it's height by width. Our input channel is going to be the number 2 because of max and average pool. And then our output is going to just be a 1 by height by width. Any questions so far? So what we have to review is an aggregation of what are the most important points, or what are the most important locations, you could say the space of every single feature. And we do that by aggregating it along the channel dimension, and we do that for a max pool and then an average pool. So what we get here are the important locations via max pool for all the channels. And then we do the same exact process for the average pool. And then we concatenate them together, so that's another form of aggregation. Except, I guess not aggregation, but it's another form of combining data without losing any data. Because aggregating, you're naturally losing data. Concatenating, you are not losing any data. And then you're doing a convolutional layer. Because the reason we do that is because we want to have a 1 by height by width, not a 2 by height by width. So in a sense, you can think of a conv layer as another aggregation, where we're taking a 2 by height by width and turning it into a 1 by height by width. Any questions on this?
Why do we want to move from 2 to 1?
The reason we want to get 2 to 1 is because we just want to have one matrix that contains all the information about the important like spatial locations of the entire input feature.
Right.
You're going from 2 to 1 because you're like concatenating the max pool and average pool into 1.
So you're concatenating it, but that doesn't reduce the size. It actually increases the size, right? Because it's a 2 by height by width now, and not a 1 by height by width.
It's the convolutional layer that deduces the size, right?
Yep.
From 2 to 1.
No.
Yep, exactly. So this is what's actually happening in the back end. We don't need to like explicitly write any of this part out, but we have a 2 by height by width as per this. We take our kernel, and because we're going to code it out as having a two channels, it's going to go over this first channel is going to go over this first one. This back one right here is going to go over to this one. And it's going to be the same exact convolutional process where every single number is going to be multiplied by every single number. So 0 and 0, 1 and 1, 2 and 3, 3 and 4. And then this back one is going to do the same exact operation on the back. And we're going to have this as our output. And then this kernel is going to be sliding over to this next one. And it's going to do the same exact process until we get our output here. And then the reason we want to, and then we are going to add them together, or the code on the back end is going to add those two matrices together. So this is a 1 by h by w, this is a 1 by h by w, and then when you add them, you're going to get a 1 by h by w. Yeah. So this green part is here. I put some just to show that we're aggregating it down to a 1 by h by w. So we're doing the same conv process as before. Instead of in this example, this is one channel. Here we're doing 2 channels. Then finally, we're going to be taking our matrix here, and we're going to be doing a sigmoid function, the exact same sigmoid function that we talked about earlier. So this should be x sub I, and then we have this, which is here, and then we have our purple, which is here. This is the last thing we want. And we're going to perform a sigmoid function on every single number here. And so every single number here is going to be a number between 0 and 1, just like we did for the vector, for the channel attention. Okay, we got some time. So, in summary, we have our f. We have our average pool, we have our max pool, along the channel dimension, okay? And then we're going to be concatenating it as per these hard brackets next to it. Afterwards, we're going to be doing a convolution. The output of this convolution here has to be the same exact size as the height and the width here, and the height and the width here. What's the... Do you guys remember the parameter or the thing that we need to keep our output shape the same size as the input shape? You guys remember what we need? Padding. So we have our hard brackets here, and then this f stands for function. It's going to be our convolution. In the paper, they use a 7 by 7, so that's why this has 7 by 7. So we're going to be doing a convolution of a 7 by 7, kernel onto this concatenated this part here. And the sigmoid is this right here. And so this is this. Alright, you guys probably know this already. Alright. I was gonna have homework as you guys code it out, but I really don't want to give you guys homework. It's messed up. So let's code it out. We're gonna be referencing, or I'll be referencing the paper and the slides. Pretty much the same thing. But let's code this out, guys. I think we need to. Let's see. I have actually. I got you guys started under Google Colab/code under module 5, the CBAM, under channel attention and spatial attention. I have like some generic code that we'll be using. And I commented it out so that I can also like look at it. So if you guys want to follow along, that'd be great. If not, that's fine. You guys can just like tell me. Like I'll be asking you guys questions, and you guys can just tell me what I should be typing in. So we have our okay. So we're going to be doing channel attention first. Remember, this is channel attention. We need to do this. So we need to do a global pooling for max and average. Okay. So I'm going to look up how to do a global average pooling in PyTorch. Adaptive pool to D. So this is the code that I get from like this AI generator, and remember how I mentioned to you guys that the shape we're going to be getting is the number of channels, because we're going to be performing this average pool and this global pool per channel. We're going to be doing a global and average, max and average pool per channel. So what we get is the number of channels here in this example. So this guy did 1's the batch, 64 is the channel, 7 is the height, and 7 is the width. They did a adaptive average pool 2D, which is what we're going to be doing. And the shape is a 1 by 64 by 1 by 1. So this is why I said to you guys, we should keep it, or I'm sorry, that's why I mentioned during the lecture that it's going to be like channel by 1 by 1. It's because of this. It's just easier to, visualize these things when you can switch between like a linear algebra explanation of the shape and then like a computer science version of the shape. But they do mean the same thing effectively. So I'm going to copy and paste this into the code. So we have our global average pooling. We can call it self.gap, and then adaptive average pool 2D. Why are we using 2D and not 3D?
Because the feature shape is 2D.
Because we have two of them. We have the max, we have the average pool and the max pool, right?
This is already the average pool. What does the 2D represent?
Within the height.
Yep. If this was 3D, then it would be the channel number from the height. But we are doing 2D. So we have our global average. Now we need our global max pool. Yep, I'm gonna Google that. How to do global max pooling PyTorch. Okay, very similar process.
Bless you.
Let's see. So it's a similar process actually. So I'm just gonna copy and paste this into our Google Colab. Get rid of this. Get rid of this. So we have our average pool and then we have our max pool. Yeah. Any questions so far on what I just did? What I just
why are there 2 parameters for average pool and only 1 parameter for max pool?
It's a great question. I don't think it matters. The reason why I think this
Oh, it's
is the
thing.
same as this,
Interesting.
as per this AI output, and this is average pool, and that's what they gave me as well. So I guess for the sake of continuity and to make the code easier to understand, I'll do that. We'll do a tuple, and this tuple I'm assuming is going to represent the output shape, which is a 1 by 1 of what we actually want.
Right.
Hence global. If this was a 2 by 2, this would not be a vector. This would just be a channel by 2 by 2. Make sense?
Makes sense. Thank you.
Okay, so after this, what's next, guys?
The autoencoder?
Yep. So let's do that here. Let's call it MLP. I'm gonna wrap it into sequential just to make it easier to like code out in the forward pass. Linear. So if you look at nn.linear PyTorch, we have a few parameters that we need to actually put in. We have our in features and out features. Oh yeah, so why is this gonna be false in terms of the paper? Let me see where I found that.
Why'd you look at inn.linear?
I'm sorry?
Why'd you look at inn.linear?
Because the autoencoder is essentially going to be 2 nn.linears. We have, and we're going to do an nn.linear for this, and then an nn.linear for this. And then in between them is going to be an activation function. So this is a rough pseudocode for it.
Okay.
So now the question is, we have an nn.linear. What is going to be the in features and what's going to be the out features? Out features, I can just tell you guys that. In the research paper, let's see. Let me see if I can find it. Okay. The shared network is composed of a multi-layer perceptron with one hidden layer. This is what you mentioned, Jamal, the one hidden layer, right? So this paper mentions that. To reduce parameter overhead, the hidden activation size is set to a channel divided by R, where R is the reduction ratio. What does this mean, guys? Code-wise, what does this mean?
Reduction ratio?
Yep.
Is it average?
So this is what it's saying here. This highlighted part is what we need to code out. How would I be able to code out what's in this this highlighted section?
Do you have to figure out what R is? The
Yep.
value of R?
Yep.
And then once you do that, you'll just pass in channels divided by that value R.
Yep, that's it. That's literally it. So to repeat what Tawny said, which is spot on, we need a way to take our input channels, or this number here, and divide it by an R, or a reduction, and that's going to be this here. This is going to be n divided by R. This is going to be n divided by R. We want the same number because matrix multiplication states that those two dimensions have to be the same. And then we're going to put it back out. This out here is going to be the same shape as this. So I already have a parameter here called reduction. So we can just use that. What are we going to type? So this is going to be something divided by a reduction, right? What do I want to put here? This underscore.
Channels?
Yep. Channels. Okay. And then in features is also going to be channels. We don't know what the channels are yet, but we are going to be just setting them as a parameter so that they can be flexible once we code them out later on. Because like I mentioned, we can put this channel attention anywhere. We can put an attention module, an attention mechanism anywhere. It could be here or here, or here or here. It doesn't matter. But what does matter is that the number of channels here is different than the number of channels here. So we need a way to make our code flexible. So instead of hard coding this like 128 or any 2 to the power, we need a way to make it flexible, so we have to call it channels. Okay, what's after this, guys?
Activation function.
Yep. The paper uses, pretty sure I know, let's just double check. Okay, yeah.
I have a quick question.
Yep.
Are you more so looking at the diagram or the math equation?
That is a great question, dude. The way I approach research papers, especially for machine learning, is I like to get an understanding of the diagram first, just to see what's happening conceptually, and then the math fills in all the details. So the question in terms of the math is, how can what did the paper, so what we just did, the autoencoder, the question I had is, how did the paper reduce from this to a smaller number? How did they do that? Did they just hard code a certain number? Did they divide by a certain number? And why did they do that? So we know for a fact, conceptually, that they went from a big number to a small number. Back to the paper, they did that by this, where R is a reduction ratio, so R is going to be this R here. So they're dividing by a parameter, or a hyperparameter, I should say. So that's how I know that they're making a number smaller, because dividing inherently makes the output smaller, unless you're dividing by a decimal, but we're not dividing by a decimal here. Yeah, that's a good question. So I'm just going back and forth right now of like, what does the diagram say, and what are the specifics? So the next question is, within this autoencoder, I need to do an activation function. I don't know what the activation function they used, so let me find out. And then in the paper, they said, shared both inputs and the ReLU activation function. So I'm going to be using a ReLU activation function. And dots. Okay, what's next, guys?
Column linear again.
Yep. What's different about this linear?
Can be a lazy linear.
It can be. It can be. How would the code change afterwards?
The input is after the small number? Or is it the output? It goes small number, input, and then bias. Instead of, alright, so better, it would be out channel, then in channel, then, oh wait, no, there's two.
So let's look at the lazy linear parameters. Let's see what they require. We only need out features, and then we have bias and other stuff, but so we don't need in features. We only need out features.
So
What do we want to be the out features?
Channels.
Do you concur or non-concur?
Yeah, I concur.
I do as well. So we can get rid of this. Instead of in features, I mean, we don't really even need the parameter here, to be honest. We can just call it channels. But for the sake of, what's it called? Features. For the sake of clarity, we'll do parameters. So you can do lazy and linear here as well. It doesn't matter. It's I guess it's too late. Yeah, it's fine. So we have our in features, which is channels. So this is gonna be like 100, and then 100 divided by r, so it's 10. So we go from 100 to 10, activation function, lazy linear, and back out to 100, for example. Cool. Any questions so far on this part? This is the autoencoder / MLP. Okay. And then the final sigmoid, this is very simple. I just did the sigmoid. So let's just see if we have all the building blocks for what we want to do. This is the visual and the LaTeX. This is the code for our initial.
What are those last 2 boxes that you didn't put anything on?
For these two?
Yeah.
This is going to be adding the 2 vectors.
Oh, okay.
This part right here. We could do this in the forward pass though, because in the forward pass, in the init, we are initializing stuff that has parameters. In the forward pass, because there are no parameters here, we don't need to initialize it in the init, only the forward pass. Okay, cool. So, the reason why I want to establish the shape here is because we're going to want to manipulate a lot of this. So, in your head, this is like very, very simple, but when you code it out, it's like a pain in the ass. So, let's get started. We can call this like x equals 2. Oh wait, you know what? Oh yeah, okay, so how would I start coding out this forward pass, guys?
Like you just did, say x equals to the new shape?
The which one?
New shape, based on what the research paper does and
The
how.
new shape? No, like
Oh.
word for word, what would I type in here?
The first thing you have to do is get the average pooling and the max pooling.
Yeah.
Right.
So we can call this x max self.gap, and the input is going to be our input tensor. And then we can call the next one xgap. Oh wait, this one should be map. This is gap. Oh, we can't call it map because map. Okay, so you guys probably can't tell. This is like a light brown color.
Mm-hmm.
This is a black color. So I think map is probably a method, like a built-in method. So we need to change the name of this instead of map. We can do it. We can call it max. And this could be max. No, max is still a method. Let's call it
Mac. M-A-C.
Max
let's
underscore.
call it global max, global
Oh, okay.
average. A little more wordy, but see, now it's black, not a method anymore, so that's cool. So the shape of this, what's the shape of this, guys? Get rid of that. What's the shape of this?
2 by 3 by 1 by 1.
Give me variables, not numbers.
Oh.
One.
BC1,
One.
1. Yep,
Mm.
that's it. Batch stands, or I'm sorry, B stands for batch. To give you give you guys a reminder, when we're coding something like this out, a couple of weeks ago, I had you guys do homework. Part of the homework was to create a data loader and a data set. Your data set looks something like this. I hope. Do you guys remember this?
Yes.
Cool. This is a data loader. Takes in the data set. And the data loader is going to be this part that takes in this training data and validation set. So in the computer, we have our data. This is going to be all the data points that we have, and this is going to be an iterable, like a list, a dictionary, it doesn't matter. A bunch of images, it doesn't matter. We have a data set, and this grabs the data in an organized way. It's more specifically, it grabs the indices of this. And if your data has the same thing called like labels, then this data set would also grab indices from here. This is one way. You could also have this also have labels. It doesn't matter. However, the shape of this data should be the same shape as these labels, because the indices need to be the same, right? So we have that. In the code that we did, all of our data in our labels is within the same iterable, the list of tuples, if you guys remember. Where this is like an image, and this is our label. And then next image, and the next label. So this is what our data looks like. So we just need to grab an index of this, for example. Then we have our data loader. Data loader is necessary because all it does is it does two things. It turns things into batches, and it randomizes. R-A-N-D. Batch is important because our computer is going to break if it looks at all of our data. It's also very inefficient to do so. So we need to take batches. These are powers of 2. 2, 4, 8, 16, 32, 64, 128, blah, 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 blah. And then we also randomize. So it takes these indices and it just like swirls them up so that when we train and test it, we can train and test on like randomized, so it's more scientifically rigorous. Tony's team had a thought because their current project has really good training but really low validation. This is very common, this isn't abnormal. Jerry had a really good idea of looking at what patients are in each loader for your training, validation, and testing loader. He thought that there could be a class imbalance or a downsample or whatever it's called. For example, if we are training and then we're testing and validating, if our training has like 80 patients, with 80 patients, 40 is Alzheimer's, 40 is healthy, and then we're testing it on another data set with 10 people with 5 and 5, that's perfect. That's in an ideal world. It's never going to be like this if you randomize it. So what you're going to need to do is manipulate something here, the data set, or something in between this pathway, so that you can purposely get an equal number. There is a way to do this, and this is a scientifically viable way to approach this, so that when you're testing it, you're getting a more fair number, you could say. Anyways, that's a little side tangent. Back to here. This is what the data loader is doing. So this batch, this B, is going to be the number all the way at the bottom that I just discussed with you guys. And that's what I want you to, that's this B. Seems kinda useless when you're talking about the model, like the research paper, and it is. It's only useful for the computer science aspect. So when we're coding it, and we want to reshape something here, we have to keep in mind that there is this B dimension, this fourth or first dimension, you can think of it. All right. Boom, boom. Let's do input shape. What's the input shape, guys? In variables.
B, C, H, W.
Yeah. B, C, H, W. And we have BC11, BC11. So there we okay. So as per the comment, we want to get rid of 1 and 1. The reason we do that is because when we do a linear, or a lazy linear, it doesn't matter. When we do a linear or a lazy linear, what it's going to be doing matrix multiplication on is the last dimension, always. The last dimension of these two are 1 and 1. The last dimension we really want to do lazy linear on is what?
W?
Channel?
Yeah.
Oh.
So we want to get rid of the 1 and 1 so that we can perform the linear on this C. So that's why I mentioned to you guys throughout the thing, it's C by 1 by 1 by 1. Technically, it's just a C or a 1 by C, you know, from a linear algebra standpoint. But from the computer standpoint, it's a C by 1 by 1. So we need to get rid of that. All right, let's Google how to do that. I forgot the code for that. I have Dude, I'm telling you,
Bro, you
like,
give me light, bro. Like, yeah, that's what.
research is not like reading something and you just know it. Like, to me, research and like just being good at solving problems is reducing your problem down to a Google search. If you can effectively reduce the clutter in your head and the problem down to a Google search, or you can just break it down to to smaller problems, that's what research is. That's what learning is basically, right? And that's how like all of our chapters are structured. You learn a chapter, and within a chapter you learn like 10 lessons. Within 10 lessons you learn like 5 subsections, and that's just really what it is. It's no different from coding, in my opinion, or just research in general. So yeah. Let's see what we got. We got squeeze, view, reshape, and flatten. I like this one because we can explicitly set the new shape. Remove all dimensions of size 1. I don't think we want to do that. Collapses the last 2 dimensions into 1. Don't think we want to do that either. What do you guys think we should do?
View.
I like the view.
Yeah, I think so too. Okay, so x max view equals to x dot view, a, b, c. Okay, wait, we should look up what view is. View, coverage. View. Let's do tensor view. Changing underlying data without changing underlying data, which is what we want. That is what we want. If anyone has suggestions, I'm all ears right now.
What do you mean? What if just use reshape though?
What was that?
Just use
Okay.
reshape.
I think I get it. So if we have a tensor with a shape of 2 by 3 by 4, this is a 3D tensor, and we want to reshape it to have 2 rows, -1 is always going to be the last thing, right? Like the last thing. That. So right now, we are still here. Now we need to enter this territory. MLP. How do I do that? What do I need to put in the code? Remember, they share the same MLP.
So x equals, or Yeah, x equals x dot MLP.
X equals to, I know what you mean, it's not, it's gonna be self dot MLP. What do I put in parentheses? What's my input?
Do you have to put anything in the parentheses?
Yeah.
Oh.
So MLP is going to be the sequential that we have.
Mm-hmm.
What's the input to our sequential? Our sequential is going to be the autoencoder, right? Right here. What's the input here? Either from LaTeX or from diagram.
Oh, that's right.
The average pull.
Indeed, indeed. So you can do this here.
Yeah.
What else?
And then the another
This
the
one,
other
right?
one.
Max.
Yeah.
Yep. So this is how we are going to demonstrate that we're using the same autoencoder for the GAP and the max. Now let's change the variable names. Let's call this x. No, let's call it max MLP. Let's call this gap MLP.
So, can I get this straight?
Yeah.
So is this the decoder, or are you calling the MLP again?
Same thing.
Hmm.
So the variable name is called MLP because that is the umbrella term. The more specific term for this type of architecture for this MLP is an autoencoder.
But what I'm a little confused about is why are you doing it twice?
Yep, great question. So this is an autoencoder, right? This is an MLP. This is if you look at like a Neuro MLP, you have a generic diagram, you know, that we've all seen, you know. This autoencoder is just one variation of that, where you're reducing the size and then expanding the size outward.
Oh, okay. So this is two different parts of the same MLP.
Two different parts.
Okay, so the first MLP where you have it commented, MLP bottleneck reload projection. Then after the final sigmoid, pooling shape, remove spatial dim, then you have the second MLP. Based on the
Do you mean here what's highlighted?
yeah.
What I'm highlighting here?
So based on this,
Yeah.
I thought it was after average max, then you have the MLP.
Yep. So
So-
we're on that right now.
Okay, so what about the first MLP? Is this still the same MLP that we're working on? Why is there one of before? I'm a little
Do you
confused
mean
about this.
in the init or in the forward?
No,
So let me know where to stop. Like
right there. Yeah, that MLP.
Yeah. So we have this in the init method, this method, and then we have another one in the forward method.
Yeah.
The difference between the init method and the forward method is that we want to create. So the way I like to think of it is you have your data, and then you have your output, your f of x. Everything in between that is going to be like a factory, I like to think of it. So you have an assembly line with like machines. What we're doing is we're establishing the assembly line and the machines in the init. That's why I like to think of it as like init, like initialize. You're creating this warehouse so that in the forward pass, you can just move your x down this funnel to get your f of x.
Okay.
Right, so part of this means that we need to create things in the init.
So you create it and then use it.
Yep, exactly.
Okay.
Yeah. Now, I told you guys that everything in the init can be in the init because they have parameters. In the forecast, they don't need parameters. That's not true. The sigmoid function doesn't have a parameter. The global average and the global max doesn't have a parameter. I don't even know what's required between here and here. I just Google it. So like, there's a thing that we're gonna be learning called like a channel shuffle, where it takes our C by H by W, and it's going to look at the C dimension, and if it's 100, for example, and I want to do a channel shuffle, it's going to take, like, for example, 10, so we divide by 10. So now I have 100 divided by 10 by height by width, which means I have 10 subgroups, and it's going to shuffle that. That would be something you would call in the init, and then you would use later in the for. I really don't know the rhyme or reason as to what's in the init or what's in the for. I'm sure there's a computer science reason. I personally just don't know it. But essentially, we need to create our factor here. So yeah. Are there questions regarding that, init versus for, or any questions regarding what we just did here with this MLP? Oh, it's 4:07. If you guys need to go, don't let me hold you up. If you guys want to stay and finish this up, then you can do so as well. But I'll be staying for those of you who are interested, because this is some pretty cool stuff. So we're here, and like I mentioned, we're using the same MLP for the max and the average pool. So here and here. Also indicated by this research paper. Shared for both inputs. Both inputs meaning the average and the max pool. Very easy to do that computer-wise. We just set one MLP. Now, if it was like a different one, for example, we would just do this. We can call this MLP2. Or we can call this MLT for a global and then MLP for the max. But it's not that. We are using the same one. If we use different ones, I would be creating, like I mentioned, 2 of these. And then in the forward pass, I would be doing the global MLP and then the max MLP. Does that make sense, guys?
Yes.
Okay, cool. So let's get rid of that. Let's change his name. What's next? I guess it's already here.
Reshape attention.
Yeah.
Wait, do we also have to add the number of channels
Do we have
In-
to
for-
add?
as an argument when we call MLP?
Over here?
Not there, but when we're defining max MLP and gap MLP, do we need to put a value for channel since that's being passed as a parameter in our init?
I see what you mean. I see what you mean. We do not. When we run this, our model is going to have these parameters, channels and reduction, and these parameters are going to exist to live in the init function.
That's basically the object constructor for.
Oh, that's right. For the model.
That's
Oh,
what it is.
okay,
It's
okay.
the Python version of the object constructor.
Right.
So it's
Okay.
already gonna happen when we create it.
That's right.
Word. Don't even know what that is, dude. No, I know a lot.
That was perfect, bro.
Yeah. So, we have a. Oh, okay. Question. So, what's the output shape of this?
Well, we have to add both of them together first, don't we?
Yes, we'll get to that. We'll get to that. What's the output shape of this and this? They're the same thing. The output shape.
Just BC.
B, C. You guys agree?
Yeah.
It is. It is. Okay. Now we have BC. We want to turn it back to BC 1 by 1. Why is it important that we do it 1 by 1 and not just leave it as BC? Think a few steps ahead. What do you want to do at the very end of this?
Aggregate it.
Well, you wanna take the final, what is it called? The final attention thing and
Yep.
apply it with the original.
Yes. So we want to do that. That's exactly correct. why is it a problem if we multiply B, C, and we multiply by our original input shape? Why would that not work?
You can't multiply
They're
them.
on the same dimensions.
Yeah, exactly. So our original dimension, right, is B, C, H, W. Right now we have B and C. We want to add more dimensions so that we're not multiplying a 4D by a 2D thingy. It has to be 4D by 4D. Has to. Not matrix multiplication actually, because we're using element-wise multiplication. So we have, okay, it'll be easy for you. Matrix multiplication is and in the linear. What we're doing is element-wise multiplication. Remember this, where we have this number here is multiplied by this first one. The second number is multiplied by the second layer, and the third one is multiplied by the third one. So every ith value here is multiplied by the ith channel here. So that's how you do it mathematically. Computationally, what we really actually need is for this to, in the computer sense, to be a 4D matrix as well. So we're having a 4D matrix, or I'm sorry, in this example, we have a 3D matrix, and then what we really need is technically a 3D matrix, although it does look like a vector, and those 3D matrices are going to be multiplied element-wise together. Does that make sense?
Yeah.
Okay, so back to reshaping. So we need a 1 by 1 by 1. Let's see. Let's go with this. How to add dimensions to a tensor. Okay. Unsqueeze, new axis, reshape, or view. I think we can use view. It seems a lot easier. We can just literally add the number 1. So in this example, if we have a 3 by 4 tensor, if we have a 2D tensor, and we want to add another dimension, we can just add the number 1. And we're also just going to be using view. We used view before, so I think we should use view again. So I'll call it gap reshape equals to gap MLP.view. What do I type in, guys?
B.
Same. I was thinking, but my confusion doesn't matter if the one is in the front or in the back.
It does matter. Yeah, it matters.
Yeah, so I don't know how you would compensate for that.
Would it just be BC11?
Yeah. BC 1 and 1.
Oh, I thought that because of how it showed you the one was in the front, that you couldn't move it to the back.
Oh, you could definitely move it to the back. The difference between this would be in this generic example, if we have a 3 by 4, if we have a tensor that's 3 and 4, height and width, we want to add a channel, we would do it by adding this. Now, if this was a channel and this was a height, and we want to add width, for example, then 1 would be at the end. And that's exactly what we're doing. We have B and C already, which is going to be here. We initialize those variables in the very beginning. And so we have a BC11 using view. So I'm going to copy and paste that, and then we can do max reshape, max MLP, there. Okay, element-wise sum. How to add two tensors of the same shape. Torch.add, the add operator, or torch.add. Add operator sounds the most simple. You can call this out equals gap reshape plus max reshape. So this adding right now is over here in the pipeline. this part. We just ran through our MLP, so we got two vectors. We added the shapes back to it. We added the 1 by 1, which is the height and the width, and then we are adding them together. So this part right here slash this part right here. What's next?
Sigmoid function.
Yep. So how would I code that out?
There's a, isn't there a formula for it? 1 over,
We can do a formula, but I initialized sigmoid in the init. Actually, let's see. I'm thinking like we might we could do it by hand. Nah, that's crazy.
I mean, yeah, that's.
That's not how.
Every time I see that, I think of arc tangent.
Like on the side, kind of.
Except it doesn't go
Okay, so like I mentioned, guys, we needed a 4D multiplied by a 4D. A 4D multiplied by 40. So we have it here. This is going to be 4 dimensions, where we have B by C by 1 by 1. It's like that because we're adding the two vectors. We're not concatenating them. If we concatenate them, it would be B by 2 times C by 1 by 1. But since we're just adding it, it's going to be BC 1 and 1. Like this. Okay, so now what are we multiplying? We're not multiplying X by W. This is the wrong code. What are we actually multiplying? What variables do we need to multiply?
Max reshape and gap reshape.
So what are we multiplying here?
Well, out is like the final attention module, the final thing that you're trying to get. So you multiply out with the original input.
Yes. So we doesn't matter. So our original input is going to be X. So X here. So X is multiplied by what?
Out.
Yep. And then we can return final out here. And then let's see if this runs.
Let's go.
I think
Yeah.
input is call it self.sig instead of self.sigmoid. I don't
Good
know.
catch. That would definitely make it wrong. Okay, so this is the code that I have to test. I initialized a random 4-dimension tensor. It's 4 dimensions because there's literally 4 numbers here. In this general example, we have a 3, which is the batch, 16 is the channel, and 128 and 128 is the height and width. This is going to be the model. The channels is going to be, yeah, I should delete this. Okay, doesn't matter. What is this number?
That's the number of channels, right?
Yep, it is. What number is that here?
16.
Yep, it is. Okay, there's an issue, not an issue, but this is 16 and the reduction is 16, so it'll just be 1. It seems like a very small number, so I'm just gonna turn this into like 32. Yeah. 32, so if we do 32 divided by the reduction, which is going to be this MLP part, remember? If we do channels divided by reduction, this is going to be the out features. So this is going to be 32 to 32. Make sense?
Yes.
Let's run this. I knew we were gonna get an error. There's always an error. It's crazy because like this, it didn't even get to this part. It didn't even get to this part, which is like comparing the two. Anyways. Empty combination of arguments got tuple. So this is wrong.
Mine.
I think we need to hard code the number, honestly.
What?
Hard code the number. No?
But it should be the same.
Why is that the code is correct? It
That's
literally
right.
tells you the code is correct.
Very right.
Oh,
Huh?
Hers red.
The code
Yeah.
is
Yours
correct.
is correct?
Mhm.
Yours is the same exact as mine?
Pretty sure.
Empty receipt,
Wait,
down,
wait, wait,
combination
wait, wait,
mark.
What you get first? Like,
Wait, if maybe the shape is equals to output shape.
Operators here.
It's the shape. There's no problem with the shape. Right.
Nope.
So what's the problem?
Oh, so something here, I think.
Oh,
Wait.
oh, I did 2 slashes. I did the floor division instead of, yeah.
Hmm.
Oh wait, did you?
Now I'm getting another error
Oh,
here. Gap
Reshape.
reshape. Yeah. Okay, perfect. Tensors are identical, therefore code is correct. This if statement says, so we need the same exact shape, right, from our input after this. So that's what I'm doing here. I'm comparing the shape of the original 4D tensor by doing this dot shape, and then the output, which is going to be this. It outputs a tensor, and then this tensor has a method called shape, and so I'm just doing, if the shapes are equal to each other, then print that they're correct. If they're not, then fix the code. So this is channel attention. I will continue with spatial attention. Okay. For channel attention, I do have the code, the same code, but I'm not going to copy and paste it because the comments were helping me too much. So I'm just gonna copy this part, and then I hope you guys don't look either. I'm cheating. And then you can copy this. And instead of CAM, you can call it SAM, which is Spatial Attention Module. Okay. And then we can define a forward pass. So let's start there. Self and X. And colon. Alright guys, what's first? What should I type into Google to do what we want to do?
Well, we need max pool for spatial attention
Yes.
and average pool.
Yeah, but if I type that into Google, they're not going to understand that specific instruction. What do we want that's different for spatial attention versus
We want to
channel
go.
attention?
We want to go along the channels and get a vector
No, not get a vector, but do it along that vector.
along
Yeah. So, average pool along channel dimension. All right, you guys tell me. Is this what we want? Why or why not?
I think we can use torch.mean, but dimension shouldn't equal 1.
Is this wrong or is this right?
The exact syntax?
Yeah, the syntax and the output shape.
It's wrong.
It's wrong. Who concurs or unconcurs? Okay, so look guys, we want to do max and average pooling across this. Right? Across this vector. And what we're going to get is a matrix. Right? So what's the shape of this matrix? Not in terms of linear algebra, but in terms of the computer. What do you think this matrix would be? This one right here.
1 by h by w.
1 by h by w. Who agrees with that?
The shape?
Yeah, the shape of this. So we're going to be doing max and then average pool along the channels, on this vector. Imagine this is a vector. We're going to do that for every single quote unquote vector, which is a pixel, and we're going to get a matrix. What's the shape of this matrix?
H and W, H times W.
It should be a one HW net.
Yeah, so Tawny and Oscar and you, to a certain degree, are correct.
Mm.
So, is this not what we want?
It is. Should batch also be one?
Yeah, so batch is also. Well, batch is 1 because this is 1.
Okay.
Bye, Andy.
It's going to answer.
So whatever number this is, this would change. So if this was like 5, this would also be 5.
Mm-hmm.
So what do you guys think about this? Should I copy and paste this or no? Look, keep looking.
Keep looking.
Keep looking? Who agrees?
So you copy and paste, will you change the parameters? If you copy and paste.
Yeah, I would be copying and pasting this.
Oh.
Or maybe even this.
I changed my mind.
Bro, just copy and paste that shit.
Yeah, the first one.
I think that's right.
Yes, so this is correct.
Cool.
So we'll put that here. Let's title this. Let's call this like what are we doing? Average pool along channel dimension.
Mm-hmm.
In variables, what's the output shape again, guys? I'll start on B.
It would be 1 by H by, 1 by H by W.
1 by H by W. It is. That is a matrix
Mm-hmm.
with B batches. So we want to do the same thing. Instead of doing a pool, instead of doing an average pool, we want to do a max pool. So I'm just going to change my Google thing to max pool along channel dimensions. Okay. Does this work for what we want to do, guys?
Yes.
What gave you that answer?
Because the output shape for
It's
max
one,
pool,
one.
the output shape for max pool should be the
Same.
same. Yeah.
Yep. Indeed. This does look about right. Let's call this max.
What about the indices part?
We don't need indices.
Yeah.
Okay, this is good. This is good. After that, keep then is true. Is true. All right, what's next, guys?
Do you have to concatenate those two outputs?
Yes. Concat two tensors and torch dot cat. Oh, also, we actually won't be doing this in the init. We should be doing this in the forward. I
Oh yeah.
remember that we need to do in the forward. I forgot why, but this is something we do in the forward pass. So anyways, but we can continue on for sure.
Mhm.
To concat. Okay, so this is what we're going to be doing. I'll be copying and pasting this. Results, we can call it concat pool. And then we take our average, and then we take our max. What dimension are we concatenating on, guys? The default is 0. Is that, can we keep it at 0? Yeah, we're concatenating this B1HW and this other pool, this average and max pool, and we want to be concatenating against the dimension. The default is 0, so we can either keep it as 0 or we can change it. What do you guys think?
Well, I mean, because when you add the two pools, you're basically So like each pole, the C is 1, and then the height and the width is whatever it is. So when you take two of them and you add them, you're adding each pixel by pixel, right?
Yeah, so like visually, like, so would it look like this? Would it look like this? Or would it look like this?
So it would, so you would have to, you're adding, what am I trying to say? I think you have to skip the batch number, right? So yeah, it would have to start at 1, right?
So you wanna concatenate along this dimension, this one right here, right? Yeah, this one. Do you guys concur? If not, we can just keep going and then we can figure it out in debugging, in the debugging phase.
Just keep one.
Sure. What's next?
Convolutional layer.
Yep. And that we can put in our init. So we can call it self.conv. I think there's only one conv, so I just call it regular. Now let's do conv2d. Let's check out some of the parameters that we need. File not found. Damn. Okay. What? I think they.
Whoa, that's weird.
What?
What happened?
The documentation for it is a 404 page. This is crazy because PyTorch is maintained by Meta.
Hmm.
No, Linux Foundation, I think, right now. Anyways, it's maybe PyTorch? Well, AI to the rescue. Okay, let's do this. Let's copy and paste that. Okay. Conv2d. What's the number of in channels?
2.
Do you guys concur or non-concur?
Yeah, because like the MLP, because it's
Yeah,
the
I think so.
average one.
Yeah, we'll keep it as 2. We'll keep it as 2. We'll debug in a bit if it's wrong. What's the number of out channels that we want? 1.
Yeah.
Yep. And then kernel size, like I mentioned, this was 7. Stride of 1, this is true. Now, I told you guys, how are we gonna control the output shape so that's the same as the input shape? Also, you said padding. If our kernel size is 7, our stride is 1, what should our padding be? Remember, so this is conv formula. This is the formula. W is the height or width. F is the kernel. So in our case, it's 7. We need to find out this P, and our S is 1. What is our P? For this number to be the same as this number.
And W is going to be replaced by channels.
W is going to be the height or the width.
Like 3.
3? Let's do 3. Let's do 3. Let's just see let's see if that's true. And then I'm just gonna do self.sigmoid for real quick. Okay,
Yeah.
let's go back to our concat. So we have our out equals to let's call it conv out equals to self.conv and then this. Okay, what's next, guys? Right now we just finished this conv layer.
Mm-hmm.
What's after this?
What is it, the signal?
Yep, sigmoid. We can just call it out at this point. Self.sig out. I mean, this looks right.
Output is 1. Then it's 3.
Yeah, we'll run this.
But it's
Channels is 32 because it's the same number here, and reduction is 16. So let's run this. I'll just go to error called channels. Oh, I guess we call this channels. Do we even need a parameter?
I don't think so.
Like, I don't think so either, right?
Because it's always, the input's always two and the output's always one, so you need channels.
Yeah.
For the convolutional.
Yes, yes. I'm wondering how we.
Because when you initialize it, you just need the kernel size, right? And then when you create the actual input tensor, that's where you extract the average point maximum. So you don't need channel.
Yeah, because like the channels like inferred automatically by that. I think you're right. I think you're right. So we should get rid of this. I don't even think we need reduction. What parameters do we need? Oh, kernel size. I guess we can do kernel size
We
7.
don't need reduction.
Kernel size
Channels.
equals 7, which is this. Okay, let's see if this runs. It doesn't. Oh no, it says fix the code. Sucker. Okay. I feel like we should print the error and not this. So I'm gonna call this. Yeah, we don't need to know what the error is.
They like fix the code. Don't know where to fix.
Guess again.
Wait. Wait. Shit. What should?
Make them run.
Wait. I commented this out, and it still ran.
That
Oh,
means
because
there's
it
no.
skipped the if anyway, so it didn't actually do anything after that.
Oh yeah, you're right.
Oh, okay. So what we should do is print the shape then.
Yeah.
Okay. Let's print the shape. Let's print fix the code. Print fix print. We can do an F string of output shape is output dot shape. Indentation. What's wrong with indentation?
I got that too.
Okay, we have a 3 by 1 by 128 by 128. What's wrong with this? What number is incorrect? One number is incorrect.
Is it 1, 3?
It is 1.
Oh.
What number do we want instead of 1?
So we want 32, right?
Yep.
Oh.
So something's wrong. Let's figure out what's wrong.
Where's our initial again?
What's wrong, guys?
Like the initial shape.
What do you? I mean, I don't know. I'm asking. I'm like genuinely asking you guys. What does the 1 represent now?
The channel?
It probably represents the channel, right?
Yeah.
So we have just a channel. If the channel is 1, what do we have? It's a standard matrix, a height by width matrix,
Oh,
Yeah.
right? So we have a 128 by 128, which is correct because that's what we have here. So we did the convolution, we did the convolution part right. So our padding is right. That's what we can infer right now.
We didn't multiply, right?
Something like that. We did multipliers.
Wait, can you go back to the forward?
Yeah, I think.
Yep.
Yeah.
When you said, like underneath sigmoid, it just says out equals, so you didn't actually multiply by the original.
Oh, that's right. Like x equals to out plus f, right?
Mm.
Like this?
I think so.
Plus. Oh, is that plus?
That's the times.
Or is it times or plus?
Yeah, you have glasses too.
Okay, I mean it's times, but we should.
Okay, let's see. Actually, shapes are identical, therefore comes from. Yep. Great stuff.
Into your vision.
Okay, so I know I went over, but this is correct. I'm pretty sure this is correct. Not that hard. I don't think that was that hard.
What was your hardest paper that you've done? I'm guessing the one that you're working on now.
I would assume
Don't
so,
you
yeah.
go up and up and up?
Yeah.
Or something a little bit more. I can't find my phone.
Right here.
Oh yeah, I was over here looking for it.
Where's that button?
Hey, I went find my phone. I thought I left it in the bathroom. I was like,
Oh no.
no, that's good.
Okay.
this is the data structure that I'm working on. I'm trying to find. Okay. So this part,
Oh,
the one,
yeah.
I love math. I love seeing like math symbols. So this paper or this type of neural network I'm using has a lot of math involved. Makes it very fun. These are like these four are like so G has a graph. So graph. These are graph neural networks. And these are just like different variations of graph neural networks. But anyway, that was going off topic. We have our channel and our spatial attention. Next week we're going to be going into shuffle attention. And if you guys actually want to look at the paper, you guys can. It implements both a channel and a spatial attention here. So what we do is we split it up. We do a channel and then we do a spatial attention. I'm doing it a little bit different because my channel and our spatial attention is going to be more complex than what they did. What they did is like a lot simpler, to be honest with you guys. The reason why I made it more complicated was because I wanted you guys to understand the more difficult version, and we are going to be using the more difficult version. So we already coded out, if this is the architecture, we coded out the green, and we coded out the blue. All we need to do is just code out the purple, and then we're done. So that's what we're going to be doing next week.
So this is the shuffle?
Yes.
Shuffle attention.
So, and then I was reading through the paper, and the paper. So the first part of the one that we just did, was it the LeNet?
No.
Oh, they didn't use LeNet.
So I will get to you. If you guys want the code, I will be copying and pasting it onto the Notion. You guys can find it all there. So there are a lot of ways to go about attention. You guys don't have to do the way that I did it.
I guess one of my questions would be, like, what, like, if you got this down pat, what do you think you're gonna do in school? Like, like, I guess, do you feel like you're going ahead? Like you're getting the stuff before, because of course you're gonna do statistics and learning about deep learning, but do you think what you're learning right now is ahead of what you'll learn in school?
I think what I'll be learning in school is like the fundamentals of the math, which is what I enjoy more. So like, as we previously mentioned like last week, where the DeepSeek team took a very cookie cutter, everyone uses this, you don't really fuck with it, you don't touch it, it's the best already. They took that and they made it faster with linear algebra, like purely linear algebra, right? And so that's what I want to do. I want to like really deep dive into the math behind it, because right now all I'm doing is replicating other people's work and their like strategy of how to increase performance, let's say, right? And that's what I want to do as well, obviously, like to get better accuracies for like Alzheimer's prediction. But I would like to do that. All of what I showed you, very little math, right?
Yeah.
It's a lot of computer science. There's a lot of coding and like understanding the tensor shape. So that's a lot of what machine learning is. I enjoy doing the math behind it more, I would say. And so that's what I think I'll be exploring in school more.
I guess it'd be more like an understanding of the math, because you kind of don't do it, right? You just know it, and then you input it in the program.
Kinda. I mean, it really depends, because like the DeepSeek V14. If you can look at the paper, they use
No, you didn't go.
I forgot where,
I got it.
but it didn't mention. Okay, I can't find it.
I guess that is pretty interesting how they take math and like pretty much crunch and almost like brute force get better outputs.
Yeah. So they use something called like a sparsity allocation problem, and that is going to be a math problem if you guys look at the paper, but it's a lot of like understanding what's going on between like tensors, the linear algebra behind it, like matrix multiplication essentially, and seeing if there's like a faster way to skip some of this overhead and to do this function instead of this function. I want to explore that, and I want to like be able to just like
It's like optimizing.
Yeah.
Essentially, you're just trying to, pretty much bring big old space and time down,
yeah.
and save time and money, space, time and money.
Yeah. There's this other paper that came out a couple of years ago called Physics Informed Neural Networks, or PIN. And they use partial differential equations on matrices to do something. I honestly don't even know. I couldn't even try to. Yeah, thank you for coming here. I couldn't even try to understand what's going on in this paper, if I'm being honest with you guys. This course itself is like an upper division math course. But they use this to solve what we're trying to do. Better accuracy, lower compute, right? So there's a lot of different ways to go about it. Linear algebra is like the bread and butter, but you can also use, like in this case, you can use partial differential equations as well. Yeah.
That's interesting.
Yeah. And this is just one thing. Like there are so many others. I know that a lot of physicists are getting into this problem because wow. If we look at the cost and landscape, remember this is a 3D version, but my version was we want to get this circle down to the bottom, right?
Lost that.
Yeah. So this is a 2D version. This is a 3D version. Of course, there's higher ND versions, and this is a hill. So this is a physics problem, and a geometric analysis problem. So both of those fields, physics and geometric analysis, are some people within those fields have tried to conquer this problem, this cost landscape problem. So we're seeing a lot of because of the exploding field, we're seeing a lot of like interdisciplinary maths and engineering come just to like solve these type of problems. So this is something that I would like to explore as well when I get older. Yeah.
I guess that's why you moved away from data science into mathematics.
Kinda. I also moved away because the acceptance rate is a lot higher for applied math. Yeah. Because the GPA just isn't, even though the GPA right now is good, the accumulated GPA is not good.
I know how it be, bro.
No, you gotta do it. Chill it.
Nah, bro, my GPA was cooked, bro. They were like,
Any questions on this class or what we learned today? Okay, cool. That will conclude it. Hope I see you guys all.